How can a scuba diver stay suspended at a constant depth while swimming in the ocean? The answer is neutral buoyancy. A neutrally buoyant object is said to have the same average density as the fluid it's immersed in. Scuba divers achieve neutral buoyancy by adding weight to their bodies, called ballast weight. The ballast weight changes the average density to counteract the positive buoyant effects of the diver's own body and equipment. This brings us to our next question. Can we find the exact amount of ballast weight required to achieve neutral buoyancy? The first step in solving the problem is to outline our assumptions and explain why we made them. For our fluid, we assume that our diver is close to the surface of the saltwater ocean. According to Encyclopedia Britannica, the density of the fluid will be 1,028.13 kilograms per cubic meter, and we can treat it as a uniform fluid. For the diver, we assume a standard dive position, and therefore the diver's center of mass and center of buoyancy are coincident. We also assume a standard physiology and optimized modern equipment, so we can get as close to a uniform weight distribution as reasonably possible. The guiding equation for this problem is Archimedes' principle. Archimedes' principle states that the buoyant force on an object is equal to the weight of the volume of the fluid displaced by the object. We also need to keep in mind that the net force on the object will be equal to the buoyant force minus the ballast weight. For a neutrally buoyant object, this should equal 0. In a realistic non-simplified version of this problem, we would need to do the integrals to calculate the exact center of mass resulting from the diver's irregular equipment mass distribution. We would also need to change the equipment placement to keep center of mass and center of buoyancy coincident. There are two different methods we can use to find the ballast weight. In case A, we use our knowledge of the volume of the components to calculate the weight required versus the actual weight of each component to find the ballast weight. In case B, we use our knowledge of the behavior of a neutrally buoyant object to figure out the ballast weight through observation. The steps for case A are as follows. Step 1. Find the volume using the displacement of water from the fully submerged components. Step 2. Use the equation density is equal to the weight needed divided by the volume of the object, and we solve for the weight needed at the given depth. Step 3 is to find the difference between the weight needed and the weight actual for each component. This difference in weight is the ballast weight required for that component. We then sum all ballast weights to get the total ballast weight required. The issues with this approach is that it's impractical for large objects and requires knowing the exact weight of all components. For case B, we operate on two givens. First, the neutrally buoyant object shall remain suspended at target depth unless acted upon, similarly to a block at rest on a table. The second given is that a neutrally buoyant object will not exhibit self-righting behavior. The first step of case B is to establish a datum at target depth. The second step is to isolate the components. Step 3 is to gradually add weight, usually in the form of lead beads, to each component until they exhibit neutrally buoyant behavior at the datum. We then sum all of the weights to get the total weight required to achieve neutral buoyancy. The issues with this approach is that it's incredibly imprecise. To sum it all up, why is this important? Well, in case B, we looked at a secondary testing method we can use to find buoyant force when exact computation of the various properties of an object just isn't realistically feasible. We also talked about a method to find buoyant force when many values of an object may vary across trials. Buoyant force comes into play when trying to discern how submerged objects respond to hydrostatic pressure, as certain compressible objects will have their volume and consequently their density changed by the increasing hydrostatic pressure as they get further and further submerged. Buoyant force is also used when analyzing sediment flows and in general naval design. With an increased push to place major infrastructure offshores, it'll be important for the engineers of the future to understand not just how objects behave at the surface of the ocean, but beneath it as well.